Okay, welcome to VSPG, everybody. Today we have a presentation by Dr. David Catling from the University of Washington in Seattle, Causes and Consequences of the Rise of Oxygen. So the announcement I have is that next week, our presentation and for the rest of the year, the presentations are going to be at 5 p.m. Pacific, 5 p.m. Pacific time rather than 8 a.m. Pacific time. So I'll send an extra reminder or two next week, just so that everybody's on the same page. Because, well, it's mostly so I don't get everybody's emails asking me why I'm not on this Zoom meeting. But with that, I'll go ahead and Andre, do you have anything you'd like to announce? No? All right. I'll go ahead and I'll go ahead and introduce David for us. So David Catling is a professor in the Department of Earth and Space Science at the University of Washington in Seattle. His research deals with how the environment and life on Earth co-evolved over billions of years and the habitability of planets in general. He has also been involved in NASA's Mars and astrobiology programs. For example, he is currently on the science team of NASA's Mars Perseverance rover mission. As background, after finishing a doctorate in atmospheric, ocean, and planetary physics at the University of Oxford in 1994, he worked at NASA Ames Research Center for 6 years. Then in 2001, he became faculty at the University of Washington and full professor in 2012. In addition to scholarly papers, he's also written 2 books in the past decade, including Astrobiology, a very short introduction for the layperson, 2013, Oxford University Press, and Atmospheric Evolution on Inhabited and Lifeless Worlds for Researchers, 2017, Cambridge University Press. So with that, we're excited to hear from you today. David, please take it away.
Okay. As was mentioned earlier, I'm currently in Sofia, Bulgaria, where it's just gone 6 p.m. and in my hotel room. So I might just turn off my video because the Wi-Fi is kind of, well, it seems to be all right at the moment, but I'm not entirely confident in it. So let me just do that. And so I'm basically going to talk about some work that I did a while ago, and then also some recent work that was published this year, and try to put together this story of the rise of oxygen. And then just for amusement, on this title slide, I've got sort of a history of the Earth as a clock. And the reason for that is that oxygen took a long time to get up to levels suitable for large aerobic life. And of course, that's one of the issues that we'd like to explain using geochemical data and also interpretation in terms of models of the atmosphere and the Earth system. So here's the outline of my talk. I'm just going to start with some background so that we're all on the same page. I suspect a lot of people know about this subject already, but I just wanted to put it in some context. So why the history of oxygen is important. And then the second part is about causes of the rise of oxygen, the how and why, starting with some principles of redox change. And then the third part is about consequences of the rise of oxygen, and also, how things changed between before and after. And that's one way to think about the consequences, and how things may have led to the rise of oxygen and these consequences. So let me start with part 1. Why we care about oxygen through time. And one could talk about oxygen as a precursor to large multicellular life, and that includes the presence of the ozone layer. Then, of course, there's finding life elsewhere through a signature of oxygen on exoplanets. And then for the Earth, there's the connection to the faint young sun and Earth's climate history, when you have major changes in a gas that affects other gases. So part of the reason we care is related to so-called Darwin's dilemma, why we don't, or at least his perception was that we didn't find rich fossiliferous deposits prior to the Cambrian, which is a big puzzle back then, but then began to be answered starting in the 1920s when McGregor discovered iron in Zimbabwe in ancient sediments was not as oxidized as today's rocks. And that was really the first inference that there was little or negligible oxygen in the early atmosphere. And since then, we've put together this story based on geochemical data of the Great Oxidation Event beginning about 2.4 billion years ago, and then the middle part of Earth history, where oxygen is still at some low level that is debated, and then a neo-Proterozoic rise of oxygen, perhaps a further rise in the Silurian to Devonian, and then a peak in the Carboniferous, and then where we are today at about 0.2 bars. So why did oxygen have this history? Why was the Proterozoic where it was, or what was the level of oxygen in the Proterozoic? How did this dynamics play out? And of course, the Great Oxidation wasn't that great because we still had to wait a long time to all of the events we see at the end of the Proterozoic, particularly in the Ediacaran period, where I've just put some of the things that happen in the fossil record, such as the first possible animal remnants in various ways, and then Ediacaran fossils, of course, bilaterally symmetric animals, first vertebrates, first predation, etc. And of course, we talk about the boring billion before that. So taking this quote from Roger Buick's 95 paper, never in the course of Earth's history did so little happen to so much for so long, is a good phrase to quote. And why did oxygen remain low for so long? Why did it rise? The other reason for caring about oxygen is that it really sets constraints on the size of life, the size of aerobic life. Even if you have, let's say, up to 1% of oxygen, and let's imagine that the first multicellular organisms started from some lumps of aerobic cells. Well, those lumps would be size limited by oxygen diffusion to the innermost cell, and that sets you at a limit of hundreds of microns. So you can't grow any bigger than that, those kind of lumps of cells. And it's unlikely that such small objects would be able to do much in terms of getting complicated. It's not until you're at the millimeters or centimeters that it becomes possible to maybe circulate water through some kind of system. And then once you get to that scale, it's possible for cilia to transition into muscles. And then you basically have all sorts of runaways become possible: circulation, pulse, an arms race, trophic levels, lungs, big brains, etc. So oxygen, of course, is not the only thing. The only kind of big life that we see is eukaryotic. So obviously cellular complexity is also important in this whole story, but that's not something that I'm going to go into. And one can look at the size of life through various calculations where you consider diffusion through tissues, and those are where these numbers kind of come from. And I wrote a paper about that over 15 years ago. Another issue is the ozone layer, and that has a very nonlinear relationship to oxygen levels. One way to think about that, at least intuitively, is that to make ozone, you have to split oxygen into oxygen atoms, and then oxygen atoms have to react with oxygen molecules. So you basically depend on oxygen molecules twice. So you might expect it to be nonlinear, and in photochemistry, it is in the photochemical models. But so today, the typical ozone column in these units given here is about 8 times 10 to the 18 molecules per square centimeter squared per centimeter squared. And because it's nonlinear, you approach that even at sort of possible Proterozoic levels. You've got a pretty thick ozone in terms of column abundance, which will protect life on the surface of the Earth. Just as an aside, the ozone layer, we think of it as absorbing the ultraviolet light between 200 and 300 nanometers, but it also absorbs, incidentally, in the orange, the Chapuis bands. And in fact, you know, what's shown here is if you were to look in blue twilight, in twilight, you would see a sky which, well, it's blue today, but if there were no ozone on the horizon, you would always see like a kind of an orange haze. But in those long path lengths towards the horizon, the ozone layer is actually absorbing the orange and makes the clear sky bluer than it should be. And this has actually been proposed as a way to look for ozone in absorption in transmission at this wavelength, the orange, yellow-orange part of the spectrum. But in reflected light, you know, the way you might detect life in the future, photosynthetic life that's splitting water and making oxygen, is through some spectrum. Something like, of course, the James Webb Space Telescope can't see an Earth-like planet around a sun-like star because of contrast issues, and also doesn't have the right wavelength range. Here it's the visible and near-infrared, whereas the James Webb Space Telescope is everything from the near-infrared to the going outward to the mid-infrared, but not in this wavelength range. But if you did have this wavelength range and you could see reflected light, then you could see oxygen through its proxy, ozone, in the UV, or in the orange-yellow that I just talked about, or you could see oxygen itself, which has some lines in the red. And it's hoped that one day, perhaps the 2030s, in the telescope that comes, the space telescope that comes after the James Webb, this kind of spectrum will actually be real data as opposed to simulated data. The absence of oxygen also relates to the greenhouse effect. So without oxygen around, if there's a decent source of methane, it can accumulate to high levels and of thousands or even tens of thousands of parts per million compared to a couple of parts per million today. And this, of course, relates to the faint young sun problem. So today, if we just had a ball-bearing Earth, that's this curved line here, so-called black body curve. And today, the time and spatial averaged absorbed solar flux in watts per square meter is shown on the y-axis. So that's about 240 watts per square meters. And if we had a ball-bearing Earth, we'd be at about minus 18 degrees Celsius, but we have a greenhouse effect, mostly from water vapor and CO2, which raises the temperature to about 15 degrees Celsius. And the water vapor has a feedback, which is more linear than the curved Earth. But on the ancient Earth, let's say 3.5 billion years ago, the sun is fainter, so this absorbed solar flux is lower, and we need a greenhouse effect that's substantially greater, which is about 50 degrees Celsius warming instead of 33 degrees Celsius. And one way to do that is you have more CO2, but you can also have more methane, which is what we might expect in the absence of oxygen. So that really is my background to why understanding the history of oxygen is important. Let me now turn to causes of the rise of oxygen. And the way to start this is really to talk about what we mean by anoxic and oxic atmospheres, if we go back to basics. But basically what we mean is hydrogen or hydrogen-containing reducing gases dominate the redox chemistry of reducing atmospheres, and oxic oxidizing atmospheres have an absence of those reducing gases, and oxygen can attain some abundance as O2 if there's a source. So if you think about Mars, early Mars probably had, when it had active volcanism, probably had an anoxic reducing atmosphere, somewhat akin in its overall chemical character, at least, to, say, the Archean atmosphere. But then the volcanism subsided, water vapor in the atmosphere can still dissociate, hydrogen can escape to space and leave the oxygen behind, which in the absence of volcanic gases oxidizes the surface of Mars and turns it red with its iron oxides. And the hydrogen-bearing reducing gases are very low, so just parts per million for hydrogen, and oxygen that has an oxidizing atmosphere because oxygen can attain at least a small abundance, but enough to dominate the redox chemistry, so that it's an oxidizing atmosphere today. If we think about the Archean Earth with less than a part per million of oxygen, methane can accumulate to, that should be in units of parts per million, it seems to have been lost here, but hundreds to thousands or even tens of thousands of parts per million. And we can also have the escape of hydrogen to space, loss of the reducing agent oxidizes the planet as a whole, but that's not enough to sustain oxygen in the atmosphere against constant losses in our very active, geologically active planet. So of course it's photosynthesis that is the constant source of oxygen, but hydrogen escape sets a direction to the Earth. And of course, when we look elsewhere in the solar system, we see a lot of anoxic and reducing atmospheres, such as Titan or the giant planets. If you start at the beginning, where does Earth's net oxygen come from? Well, it's obviously photosynthesis, but of course you have to separate the oxygen and the organic carbon so that you simply don't go backwards with this reaction. And of course, the reducing power of the organics can be transferred to sulfide, which can be buried and is also a net source of oxygen. In the escape of hydrogen to space, there's various ways you could express that, but let's suppose we have photosynthesis and then the organic matter gets processed by microbes to make methane. Then you could write down an equation like this, where the hydrogen ultimately escapes and you've started with CO2 and water and you've got net oxygen. One way to think about this is a bit like burying your reducing power to space instead of burying your reducing power as organic matter to separate it out from the oxygen. But even if the oxygen is produced in such processes, it's rapidly consumed by reactions in the atmosphere with, for example, reducing gases coming from the solid Earth. So it doesn't necessarily build up. You have to reach a flux imbalance at some point and a tipping point for oxygen to flood the air. So with any atmospheric gas, you can write down a differential equation for its concentration, and that's equal to some source flux minus some sink flux. And in steady state, at some oxygen level, which is steady, this on the left-hand side, we could strike that through. There is no change in the rate of change of the concentration. So the source flux would be equal to the sink flux in some steady state. And if one or more of these fluxes depends on oxygen in some way, then essentially you have an equation which you can solve for the oxygen level if you know what all of these fluxes are. And the way to kind of simplify things down for this system is to think of the sink fluxes as being oxidative weathering, and then a bunch of fluxes in red here that consume oxygen, such as subaerial reducing volcanic gases or reducing metamorphic gases. They could also be the submarine ones. So these are sinks, and then the sources are in blue here, the organic burial, the escape of hydrogen to space. And today, the weathering sink is thought to be something like 70% versus the sink on the right here from the volcanic and metamorphic gases, maybe 30%, although those numbers are pretty uncertain. But one can imagine a situation perhaps where, say, the oxygen source flux is less than today. And if it were 3 times less or so, 4 times less, then basically the rapid sink from volcanic gases would eat it up in the atmosphere, and so it wouldn't accumulate, and so you'd have an anoxic atmosphere. Or this reducing sink from volcanism and metamorphism was bigger and consumes the oxygen. So if we simplify the system down like this as a sort of box model, then of course one of the things that we know about the early Earth is that the oxidative weathering flux must have been small. After all, we don't see red beds, we see detrital minerals that were not oxidized. And so at the tipping point, another issue is that we expect the reducing gases to be somewhat diminished. And so the escape flux of hydrogen coming from the decomposition in the upper atmosphere of, say, methane or hydrogen itself is also going to be small. So the tipping point really is the competition between this volcanic and metamorphic reducing gas flux and the organic burial flux, the long-term net source of oxygen. And so basically, we expect the initiation of the Great Oxidation Event to be when this blue arrow source is bigger than the red arrow source. And so you can simply define a tipping point parameter as being the oxygen source flux, the organic burial, divided by this rapid oxygen sink flux. And when this is greater than unity, the atmosphere is oxic, and when it's less than unity, the atmosphere is anoxic. And some time ago, we tried to sort of model this, and what's shown here is a graph of the various fluxes, and the burial flux of organic carbon, the net source of oxygen, wins at the point above the volcanic and metamorphic reducing sink when this parameter goes from below 1 to above 1. And at that point, the weathering flux, which is shown as FW in this graph, becomes significant. And so on the real Earth, instead of the model Earth, you will see the effects of that. So the loss of those detrital minerals in the riverbeds, the red beds that you see, and so on, the signs of oxidative weathering. Oops. But the other aspect of this, if we think about the geologic data or the geochemical data, is that there's evidence, at least this is a consensus view, evidence for oxygen production before this rise of oxygen. So for example, you might see signs of sulfide and weathering and molybdenum weathering, which is hosted in sulfide, being mobilized from the continents and then deposited in marine shales. So if you look at this graph on the right, this is molybdenum in marine shales, and you see it increase about 2.8 billion years ago. And of course, there's various isotopic systems, such as the delta 34S that begins to spread in seawater prior to the Great Oxidation Event, suggesting the presence of sulfate. And there's trace metals. There's arguments for stromatolites in lakes that they could be oxygenic, and so on. And there's evidence of methanotrophy from carbon isotopes, suggesting that some kind of oxidant was around. Doesn't have to be oxygen, but sulfate. But where does the sulfate come from, and so on. So all of this evidence that oxygen production happened before the rise of oxygen just suggests that oxygen was held back before it was able to flood the atmosphere. And hypotheses for the timing of this Great Oxidation Event, why did it occur roughly 2.4 billion years ago instead of earlier, are to do with changes in the source versus rapid sink flux. And one can talk about the source flux increasing, various ideas about phosphorus limitation or places to bury the organic carbon on the continents, or about the rapid oxygen sinks declining, that the outgassing became less reducing until a tipping point. One way to interrogate the source flux is through carbon isotopes, to look at the relative isotopes of carbonate and organic carbon, and to try to use this data set shown here to see if there are any trends in the fraction of carbon that got buried as organic carbon versus carbonate carbon. Of course, just eyeballing it, you can see that there doesn't appear to be a huge amount of change, although depending on your carbon cycle model, you could have some change in the organic burial fraction. And that's discussed in some papers that were done by a former student of mine, Josh Krasensten-Taunton, and others in 2015 and last year. Anyway, the way that oxygen would be suppressed is expressed in this diagram, where here the yellow arrows are the sink fluxes, and the blue arrows are the source fluxes, or we can think of those as equivalent, molar equivalents of long-term organic burial. And on the left, these arrows don't match. So you're going to have excess reducing power. You can have reducing air, and then the excess hydrogen has to go somewhere, and it leaks to space. So that's the steady state. After the Great Oxidation Event, you'll see that this oxygen blue arrow is bigger than the rapid sink. Therefore, you have excess oxygen, but oxygen will then accumulate to some level where another sink kicks in, and that's the oxidative weathering sink. So that's the way that I view the way that the sources and sinks works. You can gain perhaps more insight into this if you think about the various steady states. So let's think about the anoxic atmosphere steady state. So we don't have significant weathering, oxidative weathering, but these other fluxes are in operation, such as the sink from volcanic and metamorphic sources and organic burial, and of course the escape flux. And we know how some of these work. So for example, the escape flux as hydrogen has been investigated for Mars, Earth, Titan, and other objects in the solar system. So we have theory and measurements which show how the rate of escape depends upon the amount of hydrogen and bearing gases in the upper atmosphere. And if you assume that the hydrogen-bearing gases in the upper atmosphere is going to be dominated by methane because water vapor condenses out in the troposphere, and on a biologically active Archean, the hydrogen would tend to be not accumulate, but would be transformed into methane, and that's also verified by lab experiments with methanogens. Then let's assume that the reducing gases are dominated by the methane, and if we plug in some numbers to a simple linear equation which describes hydrogen escape, we can actually, which depends on the concentration of methane, we would get that the methane concentration with these numbers, which are just example numbers, not necessarily the real numbers, but appropriate for the kind of imbalance we expect, we get numbers that are thousands of parts per million of methane. And that makes it a significant greenhouse gas compared to today. And then oxygen, you can think of a gross flux, which is related to the methane flux in something like 2-to-1 ratio if the organic carbon is being predominantly used up to make methane in a gross way. Some of it leaks out, of course, gets buried in sediments. And then some residence time, which can be based on the photochemical interaction, the mutual annihilation of oxygen and methane and some rate constant, which can be estimated. And then you'll end up with very low levels of oxygen. In this example calculation, it would be at parts per billion levels and have a residence time of a few hours. One can think of this as almost like the reverse of today, where methane is at low levels and oxygen is at high levels. We might also think about the balance after the Great Oxidation Event, where, of course, the atmosphere has become oxic. So therefore, the reducing gas at lower abundance. So the escape flux of hydrogen is going to be smallish. But these other fluxes, sources and sinks are in operation. In this case, the oxygen, the weathering flux is going to be dependent on oxygen in some way, in a way which we don't really know, but let's just stick some numbers in and tune the unknown parameters to present day fluxes. And we could rationalize the fact that we would expect some low amount of oxygen. And in methane, we can estimate in the same way from some gross flux of methane and some destruction flux of of the methane interacting with oxygen. If there's a big source of methane, we can get tens in the Proterozoic, we can get tens to maybe hundreds of parts per million if there's a big source. And that can, I'm not going to talk about that, but there's various ideas in the literature why the source might be bigger or why it might not. But it's certainly something that I thought about 20 years ago, that the methane might be significant in the Proterozoic. And if it is, then it means that although I've crossed it out, the escape flux here, there nonetheless is a significant escape flux if you add it all up over the billion years plus of the Proterozoic. So you can think of these oxygen as being affected, oxygen steady states of the anoxic world, the oxic world, and the highly oxic world, of being just differences in these balances of sources and sinks through time. But one thing that we can say is that in the oxic Proterozoic, probably for the suppression of oxygen to low levels, the only way to rationalize that is that there still has to be a fairly efficient sink of the oxygen if one takes the fact that the carbon isotope record doesn't really seem to invoke a particularly large change in the organic burial flux between the Archean and the typical Proterozoic. That would suggest that the rapid sink on oxygen is still quite large, and that sink flips around between oxidative weathering and minor volcanic and metamorphic fluxes in order to get to the sort of Phanerozoic state. There will also be feedbacks at these transition points. So for example, the carbon isotope record does allow there to be significantly more organic burial in the Phanerozoic than in the Precambrian. There's also feedbacks on things like methanotrophy. There's probably feedbacks on things like sulfide and so on throughout here. So in detail, there's a lot going on to affect these fluxes, but we can kind of rationalize how they should change to be consistent with what we know about the proxies of atmospheric oxygen. So now I want to talk about some recent work about oxygen and timescales at the Great Oxidation Event, and also some geochemical evidence to give some legs to this idea that I've talked about hydrogen escape in the early part of Earth history. So recently we had a paper in PNAS, and this was about the timescale of the Great Oxidation Event as regards a flip in the atmospheric redox state from essentially being anoxic to oxic. And what you have to bear in mind is at the tipping point, the atmosphere itself is a small reservoir, so it can flip from being anoxic to oxic in quite fast timescales. So we're talking about thousands, tens of thousands of years, basically. So what I'm going to show you here on the left is a graph of mixing ratio. So 10 to the minus 2, that's 1%, 10 to the minus 6, that's a part per million. And this is versus altitude, and here are a bunch of gases in different colors. So this is a higher CO2 atmosphere than today, as you expect for the Archean. But we've also got about 100 ppm at the surface of methane, which is a typical estimate for the Archean. Oxygen itself is at the surface is below a part per million, below 10 to the minus 7 mixing ratio, and being a trace constituent is not well mixed vertically, unlike it's being a bulk constituent today. Ozone, which is in purple here, is way down. So to give you a sense of scale, the ozone layer peaks about 25 kilometers altitude today at a level of about 10 to the minus 5 or 10 parts per million mixing ratio. But here in this anoxic atmosphere, we're down at 10 to the minus 10 up in the stratosphere. So there is no ozone layer. One other thing here going on is another shade of pink purple. We've got S8 aerosols. So elemental sulfur is formed in these atmospheres from volcanic sulfur gases and their disproportionation into sulfate particles and S8 particles. And of course, these carry the signatures or preserve the signatures of mass-independent isotope fractionation happening in the photochemistry. On the right here, we've got UV, a flux of photon flux in the UV. So here you can see that the surface flux is not too dissimilar to what you're getting at the top of the atmosphere because of the absence of the ozone layer. And as we go forward in time, this will change as the ozone layer grows. So let's just set this going. And so what's happened here is you've reached this tipping point where oxygen is going to flood the atmosphere. So the movie is now running. Hopefully this is showing on your screen. Initially, time is ticking along slowly. And what will happen is that the oxygen level, that's in blue, is going to grow. As it grows, methane drops. As the oxygen level goes up, the ozone layer, here in purple, that's the ozone, is growing, and it's approaching modern levels of, well, it's 10 parts per million up in the stratosphere. And at that same time, over on the right here, as the ozone layer grows, the surface is being shielded from the ultraviolet radiation. And of course, one of the other things that happened in this movie, just going back to the beginning, is that very rapidly, as oxygen rises, you'll notice that even before, even before oxygen has got very high, really, what actually happens is that the methane, oops, let's just trying to stop that at the appropriate point, is that the methane is dropping. And as the methane drops, actually, the S8 is going away even before the oxygen has grown to significant levels because the atmosphere is not reducing enough in the upper atmosphere to make the S8. And here's the ozone layer growing and blocking out the UV. So the other thing that this bears upon is this debate about the mid-Proterozoic oxygen levels. And a sample of this debate is, say, Noah Planavsky's paper arguing for less than 0.1% times present levels in the mid-Proterozoic versus another paper arguing for 4 times present oxygen in the mid-Proterozoic. Well, these are very different, and they have perhaps different consequences for biological evolution. And the big picture is, did low oxygen or something else delay the rise of the macroscopic animal life? And another kind of implication of this is if mid-Proterozoic oxygen is real and is typical of how Earth-like planets work, perhaps we could miss life on exoplanets in the equivalent of a mid-Proterozoic boring billions stage. People have written about false negatives. So our work is not to get into this debate too deeply, except to ask, well, what does atmospheric chemistry tell you about a stable minimum oxygen after a great oxidation event? Because atmospheric chemistry is based on a lot of data about reaction rates in the lab. So although it may be a model, it's heavily based in data, which is well known from studies of the Earth's atmosphere. And what we find is that basically below about 10 to the minus 8 oxygen mixing ratio on the surface of the Earth, low oxygen is stable with reducing gases being big. But there's an intermediate kind of no man's land, if you like, where small oxygen and small amounts of reducing gases make this oxygen level unstable until you get to about somewhere above 10 to the minus 4, maybe 10 to the minus 3-ish. And the big oxygen level there makes the high oxygen stable. And the way that we interrogated that was to say, well, let's simulate an atmosphere like the Archean, and let's just put some perturbations in. Maybe this is due to the way that the biosphere is pumping out methane as time goes by, perhaps due to varying on Milankovitch type timescales. And if we do that, we can vary the flux a lot, and it doesn't have any effect on the oxygen mixing ratio. It remains stable. But at the other end, when we do such a thing where oxygen is high, again, the oxygen mixing ratio may go up and down, but it remains an oxic atmosphere, even when we impose a perturbation on biogenic gases that affect oxygen. But in the middle part, even if we impose our variation in methane fluxes, say, and of course it could be other things, it could be big volcanoes going off or something, what will happen is that the oxygen will swing from being an anoxic atmosphere to being an oxic atmosphere, back to an anoxic atmosphere, an oxic atmosphere. So this then sets a minimum level on the boring billion Proterozoic level of oxygen, which has to be bigger than 10 to the minus 4-ish level of oxygen in terms of absolute mixing ratio, because otherwise it wouldn't be stable and we would have anoxic episodes, which should be marked by a return to all the signs of anoxia, including the mass-independent isotope fractionation in sulfur. Of course, another aspect of this is that we could, at the Great Oxidation Event transition itself, maybe jump around a bit between stable and unstable oxygen states, as some people have suggested. So, for example, Simon Poulton's paper in Nature suggested there might be 5 oscillations. And that's possible when you're in this kind of no man's land of unstable oxygen levels. But after you get out of that and above your 10 to the minus 3, 10 to the minus 4 oxygen level, you're in a stable regime. And so our point was that this, the nature of the photochemistry just puts a decent lower limit on the Proterozoic. So now I finally want to just turn to this idea about hydrogen escape setting a direction on the Earth and also other planets in becoming progressively oxidized. And I want to point out that there's quite a bit of evidence to back this up, and the strongest being what happens to the xenon isotopes. So the basic principle here is that hydrogen's a reductant. If you add it to something, that's reduction. If you remove it, that's oxidation. And here's a picture of the Earth in the ultraviolet at 121 nanometers. That's the Lyman alpha line. And what we're seeing here is sunlight, which is being scattered by hydrogen atoms around the Earth. Because today, about 3 kilograms a second of hydrogen is escaping from the top of the atmosphere into space. Some hydrogen is ballistically bounced. In other words, it's on trajectories under gravity and comes back into the atmosphere. But some is on trajectories which where the vertical component exceeds the escape velocity, so it escapes from the planet. So this is a real picture from a spacecraft and an ultraviolet sensitive camera. But on the anoxic Archean Earth, we've got thousands of times more hydrogen-bearing reducing gases, such as methane in the atmosphere. And so this escape rate would go up by factors of thousands. And over geologic time, that's important. If you add up all of that hydrogen loss or the oxidation it should cause, it's a lot, enough to oxidize more than all of the net oxidation we see in the crust. In fact, that you could take as evidence, the fact that we do see net crustal oxidation, but there's some other evidence. Zircon, cerium, proxy, if there's oxidation which is exported into the mantle, there's some evidence of mantle oxidation from vanadium. There's the D2H ratio of the ocean. Has that changed over time as hydrogen was lost? And then there's this xenon isotopes, which I think is the strongest support. So the Earth's crust is net oxidized. What you can do is you can look at all the oxygen, add up all the equivalent moles of oxygen, the oxygen itself in the atmosphere in sulfate, in Fe3+, in excess oxidized iron in continental crusts, and compare that with the reduced carbon in the crust. And what you'll find is that they don't match in moles. But if photosynthesis were only responsible, every mole of reduced carbon you make should be matched by a mole of oxygen somewhere. So photosynthesis alone can't be responsible for this mismatch. There's missing reductant. And one way that could be explained is if that reductant has simply escaped to space. And this mismatch has been noticed not just by me, but by some other authors. Data number 2 is that Yang et al. In 2014 looked at a cerium oxybarometer, cerium relative to other rare earth elements in crustal zircons. The data is highly scattered, but they argued for This is oxygen fugacity relative to quartz phalite magnetite buffer. They argued that the Hadean and early Archean crust was more reduced. Well, how did it then get oxidized through the Archean to where we are today? Now, I should note that there are questions about the robustness of this. And so this is, I mean, it's consistent, but it may not be the best data to support the argument. What about the D2H of the ocean? So we have to be up here to get to modern day to 0 in the delta D space. This is actually in percent rather than per mil. But when you look at the paper by Pope et al., they were looking at serpentine minerals in Isua. They deduced that for a smaller D2H ratio, that's the cyan dot here, and that implies loss of light hydrogen in order to get up to the ocean where we are today. Of course, we need to have some loss of hydrogen anyway. However the Earth started, it would have been had lighter hydrogen according to the measurements we have of the meteoritic material that formed the Earth. If you calculate how much hydrogen escape there was since 3.8 billion years ago, given this data, it's like 1/4 to 1/8 ocean loss, depending on how you calculate it. And that's on the order of 10 to the 22 moles of oxygen equivalent, which is more than the net crustal oxidation we see, but it could be rationalized by oxidant being exported into the mantle. Other data, fourth data set, is vanadium data. There have been recent papers, Olbach and Stagno looked at vanadium, so did Niklas et al. And basically the idea here is that vanadium becomes more incompatible from the igneous rocks with higher oxygen fugacity. So you can use it as a measure of redox state. And both of these papers did that. The raw data have a similar trend. They're somewhat offset for reasons which are not fully known, because, but has something to do with the fact that they're using different oxybarometers. But when you anchor both of the same data sets to modern mid-ocean ridge basalt oxygen fugacity, you get this trend since the Archean. And basically what it suggests is that the mantle in the Archean was probably down a log unit compared to today in terms of oxygen fugacity. Well, that matters because if you then calculate what the hydrogen to water ratio would be in Archean volcanic gases, it's a factor of 5 times bigger. So that's a bigger sink significantly on atmospheric oxygen that's being produced by photosynthesis. And we actually plugged, this is a little complicated, so I'm just not really going to explain all of this, but we plugged that into a model where we also took estimates of the organic burial fraction from the isotope record. And we looked at the source and sink fluxes. We estimated those through time of atmospheric oxygen. So this organic burial was our source flux, and our sink flux came from using this data set and estimating the volcanic gas fluxes, giving the trend in the oxygen fugacity. We, of course, conserve mass and conserve redox and so on. And when we did that, what we found, this is the result, this is time. And then we've got our oxygenation parameter that I discussed earlier. Basically, when you go above unity, you're oxic. And we found that that happens here when the 5% probability quantile crosses this unity line at about 2.3 billion years ago. That's just what the model came out as. We didn't really tune it in any way. That's just just came out that way, and that showed that basically means that the atmosphere should turn oxic with a 95% probability at that time. So it's one way to explain how Archean atmospheric oxygen was suppressed, just using the data, both the carbon isotope data to estimate oxygen source fluxes, and then the mantle redox state data to estimate volcanic gases. Finally, before I get to summing this all up, there's this very unique data set where essentially Bernard Marty's group in France are looking at fluid inclusions in Archean rocks. So they include, they basically are inclusions of ancient seawater. And from those, you can look, they can back out xenon isotopes. So those are reflective of air that's in the seawater, and of course that's reflective of what's in the atmosphere. So xenon has 9 stable or very long-lived isotopes from 124 to 136. And the idea is that you look at the slope of that xenon isotope group, and if you normalize it to solar, so shown in the inset here, let's say that solar is normalized, so you start out at unity. And what was found in the data is that as you progress through the Archean, the xenon isotopes become heavier. Now think about how weird that is, because xenon is really the heaviest noble gas in the atmosphere. It's also the heaviest non-anthropogenic gas today. And so how do you actually lose that? How do you lose the light isotope in this systematic way? Well, one way to do that, and I was the co-author on this paper, is that at the poles of the Earth, hydrogen ions, they escape today, but if they're escaping vigorously, they could actually drag out xenon ions, because xenon ionizes very easily, more easily than krypton, which doesn't have this isotopic trend through the Archean. And so you can gradually make this distribution of xenon isotopes heavier and heavier. Now, the way that it's normally plotted is with respect to modern air. So it's kind of the reverse is what's shown in my inset here. But you can see that if we start with solar and chondritic up here, and we're plotting here the xenon isotope fractionation relative to modern air, in other words, the slope per atomic mass unit. And those xenon isotopes continue to be fractionated throughout the Archean, but the trend stops after the Great Oxidation Event, or it becomes so small we can't distinguish it from the error bars. And then basically have something very close or at modern. So this is consistent with the idea that hydrogen was escaping rapidly from the early Earth. And if you figure out what this means, it means something like tens of % of ocean loss equivalent. And 10% is the equivalent of generating an oxidation of roughly 20 bars of oxygen. Of course, that oxygen gets used up in oxidizing the crust or oxidizing the mantle. But I think this data set is interesting at a number of levels, because it gives legs to the idea that hydrogen is escaping to space. And also it tells us something else, because we have to get from solar to the first data point in the Archean, which tells us that things were escaping in the Hadean, otherwise this unseen eon of Earth history. And that means that reducing gases must have been at some level that was significant even in the Hadean. And also, the way that this works is that the xenon escapes on these open field lines, and that suggests that there was some magnetic field present even in the Hadean to make this work. We can even back out what the methane levels should have been from this data set in the Archean, and here we've got like 0.5% methane if that was dominating the hydrogen-bearing gases. And this whole theory makes sense because the krypton isotopes are not fractionated, even though those isotopes, the 6 of them, are lighter. And that turns out there are good chemical reasons for that, which is that krypton basically, if it does form ions, those ions rapidly get destroyed, so it can't be dragged out in the same way. And oxygen-rich air will also kill xenon ions, because it turns out that in the ionic chemistry that it kills xenon ions in a way that it doesn't for other gases. So to summarize, Earth's atmospheric evolution is dominated by this oxygen increase. We care about it because it allowed aerobic life to evolve, including us. This whole story started with McGregor noticing the absence of oxygen on the early Earth. That was back in 1927, and yet we're still debating about how all of this worked and the timing of the Great Oxidation today. But we can stick to certain chemical principles, which if we consider fluxes, the conquest of oxygen has to wait until the exhaustion of reducing power. One can think of a dynamic flux balance. And if we think in terms of reservoirs, if we change the reservoir of the atmosphere and the crust to be oxidizing and oxygen rich, then net reductant must have been lost from this surface environment. And I talked about the simplest global oxygen model, a balance of 4 kind of redox fluxes, couple of source fluxes, couple of sink fluxes. And this gives plausible levels across the eons and insight into the relative size of these fluxes, suggesting that oxidative weathering may have not even been the dominant sink on oxygen for most of the Proterozoic, only after the Neo-Proterozoic. And then I talked about how, I also talked about how the photochemistry requires a minimum level of oxygen to be stable after the Great Oxidation Event. Otherwise, we would expect anoxic atmospheres to appear in, say, the mid-Proterozoic due to perturbations in the atmosphere. And finally, I talked about this idea that rapid hydrogen escape was an important ultimate driver of oxygenation, setting the direction to the Earth's redox evolution and biological evolution. And at the time this was proposed, over 20 years ago, there was not a huge amount of evidence to support the idea. But since then, various lines of evidence are consistent with that idea. And the strongest one of those is this unexpected gradual loss of lighter xenon isotopes in the pre-Great Oxidation Event atmosphere. And so that concludes my talk. Thanks for listening.
Okay, thanks, David. That was really good. We're going to now transition to the questions and discussion. So you can participate in a couple of ways. You can raise your hand, which you can find that down at the bottom of your Zoom window. Click reactions. It's that raise hand button at the bottom of that little box, or you can type it into the chat and I can read it for you. We have one in the chat from Ben Johnson. He says, "Hi, David. Thanks for the talk. In your animation of atmospheric mixing ratios, the switch from low to high O2 and the disappearance of S8 happened very quickly. Some newest geochronology by Gumsley et al. Are permissive of multiple episodes of oxygen reduction around the GOE before permanent oxidation occurred. Can you speak to the interaction of can you speak to the interaction between these time scales? Thanks."
So the first thing to say is that the timescales taking place in the atmosphere are very short. So basically they would be sudden in the geologic record. They would be sudden switches between the presence of mass-independent isotope fractionation when, say, S8 is being produced versus not. So the time scale that we had there for the oxygenation of the atmosphere is on the order of, let's say, 10 to the 4 years. But if you go back to an anoxic atmosphere, how long it takes for you to get to another tipping point depends on a whole bunch of things, related to what the biosphere is doing, what the geosphere is doing, what the volcanic fluxes are doing. So that could take much longer and probably independent of the timescale of the flip that I was talking about. So I don't think there's a direct relationship between the timescale, how long it takes to flip the atmosphere, and how long the pauses may be between going from an anoxic state to an oxic state. All you can really say from the photochemistry of the atmosphere that when you do the flip, when you do reach a tipping point, it's very fast to go one way or the other. Actually, I didn't talk about it, but in the paper, we also talk about going back. So I just showed you the simulation of becoming oxic. If you go from oxic to anoxic, because you essentially put the tipping point the other way around, then You go back on a similar time scale, it's not exactly the same, but it's on the order of 10 to the 4 to 10 to the 5 years, not greatly different. I don't know whether that answers the question, but yeah.
He said, all right. He said, thank you. Yeah.
Okay.
Okay. So Jingjin, you had your hand up. So go ahead.
Sure. Thanks, David. That's a very lightning talk. I actually have several questions, but I will just ask one by one and yield to Ken if there's spare time for me, allow him to ask further questions. So my first question concerning another phenomenon at the foot of the photochemistry at low O2, whereas if you don't have enough ozone, the photolysis rate of water will be higher, so you produce much more OH and HO2, which will destroy methane. Whereas we see from your time evolution, that's a graph, the concentration of the methane is pretty stable, whereas the O2 concentration varies, but in the opposite direction as I described. So I wonder, what's the boundary condition you use for the product of the methane oxidation, namely the CH3O2 and the CH3OOH, because the concentration, both of them in the modern atmosphere are pretty much in photochemical equilibrium. So the net flux of anything related to that too is negligible. But if you treat them with different boundary conditions at lower O2, perhaps that will have different response to the methane concentration and lifetime.
Yeah, well, okay. So so what you have to bear in mind is that the OH, so basically in the Archean atmosphere, although what you say is correct, that you can directly photolyze water vapor in the troposphere due to the lack of an ozone layer, the OH level is actually less than it is today because you can generate OH in a different way in our oxic atmosphere. It actually comes from the photolysis of ozone in the troposphere, which can happen at longer wavelengths. And the oxygen can then, the oxygen atom can then interact with water vapor and it can generate OH radicals. So actually it's because of our oxic atmosphere and the level of oxygen, the level of ozone that's related to the level of oxygen, that we end up with more OH than is simulated in the Archean atmosphere. And because of the lack of the oxygen and ozone in the Archean atmosphere, even despite the fact that you can photolyze water vapor, you end up with less OH. And remember, you're also generating H, but you also got an H2 rich atmosphere. And so overall, it does not suppress methane levels. If you have a methane flux that is a tenth or equal, or I mean, it depends what the methane flux is, but even if it's a tenth of the modern flux, you'd expect it to be big actually, because you're in an anaerobic environment, so the methanogens can live anywhere. They live in the water column. They don't have to live in hide away in the sediments like they do today, and they're not. The methane flux from seafloor sediments is negligible today because it gets eaten by the methane oxidizing bacteria. But the seafloor could be a big flux in the Archean. Anyway, even with a modest flux of methane, the net concentration of methane is big in the Archean atmosphere. It's not destroyed by OH, and that's not happening. It's incorrect because OH is generated through a different pathway, which is efficient in the modern oxic atmosphere. Let me see. Did you have another part to that question? The boundary conditions in the model, of course, are essentially the fluxes and also the deposition, things going the other direction of reducing and oxidizing species. But the key variables that you can change around that can alter things, of course, are the biogenic fluxes. What were they, and also the volcanic flux. But that you can change that within reason. You could make it constant to today's if you want, but most people would tend to pump it up by a factor of several due to a greater heat flow and probably more volcanism going on. None of those things, those kind of parameters are not going to make a huge difference, but the biogenic flux, that's a significant change depending on what you have.
Yeah, thanks, Dave. That's I agree with everything you said, but a quick follow-up on the OH things. So when I running down the code, the photochemical model to the lower O2 in the Proterozoic region from 1 PAL to say point
Pressures, right. Mm-hmm.
To say to the Proterozoic level,
Oh,
I see clearly the OH concentration increases. So I wonder what is the cutoff point in terms of PO2 when you then decreasing the OH concentration due to the mechanism you said?
Well, something else happens. So you may have noticed from my animation that when oxygen rose, so methane dropped in as you kind of lead up to the Great Oxidation Event, and oxygen is actually creeping up. You can't really see it very well on the log scale as that methane is going down. But then when oxygen goes up and the ozone layer forms, that actually protects the troposphere from the shortwave UV that can generate a lot of photochemistry that ends up destroying methane. So if you have the same or similar methane flux on each side of the GOE, the methane level goes down and then it comes up again. But that depends on the flux. And people have argued, there was a paper by Stephanie Olson, and she argued that with the sulfate levels in the Proterozoic, that the seafloor would be a small source because based on her model, the anaerobic oxidation of methane would essentially suppress that flux like it does today. That's model dependent. But then you've also got the land, and you've got lakes on land in the Proterozoic. Today, the wetlands are a big flux of methane. Of course, the biology is different to what it would be in the Proterozoic, but one can imagine perhaps Proterozoic lakes. And of course, there's a paper about that. I forget the first authors at Zhao et al. Arguing that that could be a big source of methane. So how much methane you have in the mid-Proterozoic is very flux dependent, what you assume about the biogenic flux. But if it's anywhere comparable, well, if it's bigger than today, because there are these anoxic regions, either on land or in the coastal regions, perhaps, or perhaps the sea floor still is a big flux of biogenic methane, then it's possible to sustain, tens of parts per million, maybe even 100 parts per million of methane in the Proterozoic. But I think, it's hard to get direct constraints on methane. The only, one way we tried to estimate that was from looking at the Xenon isotope data, but that's very model dependent on how we model that. But there are very few constraints on atmospheric methane in the Precambrian. And that's because it's a very inert molecule. It basically does a couple of things. It can be oxidized or it can be photolized and doesn't leave much of a trace. Let's see. Do I have
All right. I think
whose question should I do next?
Yeah, our next one is Kent Condi. So Kent, please go ahead and unmute yourself.
David, I was very interested in your observation that the ocean volumes may have been large before the GOE. Should we be looking for evidence in the geologic record for greater volumes of ocean and higher sea level and such?
Well, that sounds tricky to me, but because it's going to depend on other things, right? Like, I don't know, the spreading rates and so on. And you think about the freeboard and so on. So, that would be interesting, but I'm not sure you could get it to that kind of level of precision. Could you tell that the ocean volume was bigger by, say, 25% or something in the past, given all the other variables that change and affect sea level, and given the rock record being sparse as it is? What probably would help is if somebody else could do some more. These are not easy measurements to make, but more estimates of D2H from the Archean. I mean, there's basically the Pope et al. Paper, and that's it. There hasn't been other work to try to estimate the D2H ratio. And so I'd feel more comfortable about that data if other people were able to constrain the D2H from other times in the Archean. But yeah, what you say is interesting. I mean, people debate a lot about the the sea level, more in the Hadean, actually, when we, the origin of life. A lot of origin of life people, essentially all of the organic chemists that I know of, would prefer the origin of life scenario on land, not the deep sea vent idea. And so they really need land for their various prebiotic schemes to work. And so how much land was available in the early Archean or Hadean is a big issue in prebiotic chemistry.
Yes, thank you.
Okay, there's one in the chat from Lee Kump. He said he had to leave, so I'm thinking he'll catch up on YouTube. He says, nice presentation, David. Just to clarify, in your modeling, where the 5% probability line crosses the time scale indicates where you are at 95% confident oxygen rose before that time, not at that time, as I think you said, correct?
No, I think what I said is correct. So the 5% quantile is at that time. Therefore, it means you've got 95%. The by then, well, I guess what I meant to say is that you've got a 95% confidence that by then you've got an oxidized atmosphere. So I don't know. That's just what does Lee say rose before that time? Well, I would say just by that time. Yeah. It's just a different way of passing it. But yeah, but there's big uncertainty. I mean, it depends on exactly how you interpret that noisy data set from the vanadium, and also, let's see what you also assume about outgassing over time. I mean, I've also done other studies trying to look at the carbonate silicate cycle over time and the climate history of the Earth. I didn't talk about that today, but one of the biggest uncertainty in those kind of estimations is the outgassing history of the Earth, and how that works. So, for example, some people will argue about heat flux being relatively steady, or heat flux changing by a factor of 5. In the Archean relative today, and then some people will relate that to the outgassing flux in a Q² way or a proportional way, and that introduces a factor as big as 25 just in the outgassing flux. So there are uncertainties in that, and in this game of estimating oxygen, there's also uncertainties in how we interpret the isotope record to get a source flux. And we interpret that in a simple way for that model, but you can also have a more complicated carbon cycle model for the organic carbon, which we did in a paper last year, where we were also looking at the fact that you don't mobilize as much organic carbon in the anoxic atmosphere of the Archean, because you're not doing the oxidative weathering of the organic carbon at the same rate. So your input value to the atmospheric ocean system, which people normally take as mantle, about -6 per mil, is not -6 per mil if you're not oxidizing that organic carbon on the continents in the same way in the Archean. So when you look at those kind of models, you can perhaps get a different picture where you have lower rates of organic barrel, less oxygen flux in the Archean, in which case we would drag out that transition to later in time. So, we might have that crossing point be somewhat later, maybe 2 billion years ago. So we wouldn't have our 95% confidence until by that particular time. So it's a bit of a fuzzy time. I wouldn't take it too seriously, but it's on the order of it being the right kind of time for the Great Oxidation Event based on the vanadium, these interpretations of the vanadium oxybarometer for oxygen fugacity.
Okay.
Yeah.
We're running short on time, but it looks like Greg, I think, is trying to ask a question. So Greg, would you like to go?
Yep, thanks. Dave, that was inspiring. I really enjoyed it. The hydrogen escape problem is one of those great long-term things, like the increase in the brightness of the sun, it seems to me. But what's really controlling everything is biology. And in that perspective, I've been really fascinated with hydrogen loss from Mars, which is presumably related to the oxidation of Mars as well. It also presumably had a path like on Earth, where there was tremendous hydrogen loss early when there was a magnetic field, and then the magnetic field died and it stopped. Have you thought about that at all?
Somewhat. I mean, so the first thing to say is obviously Mars is red, and most people don't ascribe that to oxygenic photosynthesis, like we describe the red beds on the Earth as being caused by a rise of oxygen and oxygenic photosynthesis. We do know that hydrogen escapes from Mars today. You know, water vapor in the atmosphere is photolyzed, hydrogen escapes, oxygen is kind of left behind in the atmosphere to some extent, although some of that also escapes. But overall, Mars has rusted and is still rusting, right? There's still some, if you think about the volcanic activity on Mars, it's not completely dead. There are some lava flows there which basically don't have any small impact craters. So the estimates are that they erupted maybe in the last 50 million years or something like that. I mean, obviously we're not seeing active volcanoes today, but on the whole time scale of the solar system, 50 million years was kind of like yesterday. But it's not happening today. But what I think is there's a very slow oxidation of Mars is still going on with this oxygen that's as a result of hydrogen escape. So that's the one thing I see. And we don't see any, you know, one thing we haven't seen on Mars, there's no black shales, right? So to my mind, that doesn't bode well for finding photosynthetic life on Mars. No stromatolites have been seen yet. That doesn't mean to say that Mars didn't have some kind of chemosynthetic life that was not as productive as photosynthesis, or indeed that Mars didn't have some kind of prebiotic evolution. And so unfortunately, I think we won't really know the answer to these kind of things, perhaps, until we have samples returned from Mars. Of course, Perseverance rover is doing that. It's caching samples, putting them in tubes, which are about the size of, you know, a stick of chalk or something, and those will be picked up eventually and returned to the Earth, where you can do the most exquisite analysis that lab techniques allow you to do. So at the moment, it's hard to say how biology would have affected the redox state of Mars, but you can explain what you see, I think, with just the inorganic side of the cycle, just the very slow hydrogen escape and oxygen that's left behind and is able to be stable at 0.1% because it doesn't have any rapid sinks on Mars. There's no, you know, hydrogen or CO coming out of volcanoes to mop it up. It's only being mopped up by this extremely slow surface oxidation. That's the way I look at Mars. Does that make sense?
Well, what I'm suggesting is we know the escape of hydrogen now from Mars. Has anybody attempted a flux rate back through geological time, particularly related to the lifetime of the magnetic field on Mars?
Yes, there are some papers that go into that, and it's thought that
can you give me a name or two?
Well, it's probably Bruce Jakosky is probably a co-author because he's the PI on this mission called MAVEN, which has been monitoring the modern escape rates. So I know he's had students who worked on this, and also David Brain at the University of Colorado. So they've tried to model escape from Mars, but you know, it's a bit more complicated than the type of escape we have today, because early Mars probably was anoxic when it was volcanically active, and it may have even been fairly hydrogen rich, in which case hydrogen can actually escape at much more significant rates. And one of the interesting things is that xenon isotopes, as much as we know about them from Mars, from, you know, trapped gases in meteorites, are fractionated, but not as much as the Earth. So somebody needs to, we haven't done it yet, but that's a problem waiting to be looked at, to think about how that happened, because maybe it tells us something about the magnetic field. I have been trying to engage some people who study, you know, sort of ionospheres and people who really have these 3D hydrodynamic models to get involved in this, because one of the things that I'm interested in is, it's degenerate between how much hydrogen-bearing gases are there and the magnetic field. But in principle, you could say something about the magnetic field of the Hadean from the Xenon isotope data, I think. So that would be interesting to look at, but it's a type of modeling which would require me to do another PhD in a different subject. So I'm not going to do it.
Always. Thanks. Great
try and
answer.
understand the magnetohydrogen.
All right.
Yeah, but there are people who, that's what, yeah.
Sorry, I think I cut out for a second, couldn't hear. Okay, so David, how are we doing on time? Is there time for a little bit more?
I think it's well, it's 7:21 here. It's got dark all of a sudden. So
okay.
I could easily go for dinner at this point.
All right, well, let's let you get moving then.
All right.
Thanks so much, and thanks everybody for the discussion. And see you all next week at 5 o'clock, not 8 o'clock Pacific time. So take care, everyone.
All right. Thank you.